Christy couldn't be here today, so I'll do the introduction today. So it gives me great pleasure to introduce Dr. Joshua Heyne. He serves as the director of the Bioproducts Sciences and Engineering Laboratory at Wazoo Tri-Cities, the co-director of the Wazoo PNNL Bioproducts Institute, a joint appointee at PNNL, an associate professor of mechanical engineering at Washington State University, and a Battelle Distinguished Professor. Dr. Heyne has dedicated over a decade to advancing sustainable aviation fuel technologies. His distinguished work in green energy has earned him multiple accolades, including an EPA Green Chemistry Award, an ACS Rising Stars Award, and a Leadership Award from the Commercial Aviation Alternatives Fuels Initiative. Josh, thanks for coming today. Please go ahead.
Thank you very much. Christy, the department, all the department folks that I met throughout today. Really was a pleasure spending time with you here at UW. So as a bit of a primer, I emailed Justin asking for kind of what to focus on with this presentation, and so I got a task order of high-level things to cover, as well as some of my own research, but we can go back and go into details after I'm done if desired. So one of the things I did spend a bit of time about today is talking about where I am and kind of what's unique about one of the titles I have at WSU and PNNL. And that's the co-director of the WSU PNNL Bioproducts Institute. It's one of three joint institutes between WSU and PNNL. And what runs between all three of those joint institutes is joint graduate studies, DGRP programs, joint projects between WSU, PNNL, and joint appointments. And so there's 13 joint appointments within this joint institute, going from and to each institution. And then finally, what's unique about the Bioproducts Institute is a shared space. So this is where my lab is, and in Richland, Washington. The space is split almost exactly 50-50 between WSU and PNNL. And so it's been a really great partnership with PNNL over the last many years. There's lots of distinction in this building and within the Joint Institute, especially in sustainable aviation fuels. So as a little bit of background on my lab, we'll touch on some of this a little bit later, but what we really do is we're known for testing novel sustainable aviation fuel candidates. So, in aviation, it's safety first, safety last, safety everywhere in between. So you can imagine that for novel sustainable aviation fuels, everything about those fuels has to be equivalent or better than conventional fuels. So naturally, to prove that out, there's lots of testing that's required. And that testing requires lots of volume. And so what my lab's been able to do over the last 10 years is develop a tiered testing program at very low volumes to give research labs, academic institutions, as well as startup companies as much information as possible at the earliest stages of their technology development as possible to get them accelerated. To date, we've received over 250 samples from 36 institutions across North America, Europe, and Australia. Many of these companies have been able to raise tens to hundreds of millions of dollars, or hundreds of millions of dollars collectively. And the other thing that we do in the lab is we use all of our data that we've been generating and doing a lot more fundamental type work to make predictions. So how do you develop a sustainable aviation fuel that is drop-in, i.e. it's backwards compatible with all existing aircraft, infrastructure, engines? How do you make that fuel drop-in while minimizing the environmental impact, right, to humans and the environment? And so we've been developing these tools to make predictions over the last decade, really. And then lastly, we spend a lot of time working with early stage companies and disseminating knowledge. I serve as a co-chair under CAFE, which is the Commercial Aviation Alternative Fuels Initiative. It's a public-private partnership with roughly 650 institutions and more than 2,000 individuals. We hold webinars and educational events discussing some of the issues within SAF, as well as just how the field works writ large. So aviation, like many other industries, is undergoing a transition. There have been international as well as national commitments to net zero carbon emissions by 2050. So just an example here is the International Civil Aviation Authority, ICAO, has a long-term aspirational goal of net zero carbon by 2050. Airlines for America, that's the trade organization for all the airlines in the US, has committed to a 2050 net zero CO2 emissions. And the US government has initiated what's being called the SAF Grand Challenge, Sustainable Aviation Fuel Grand Challenge, with two goals. First one being 3 billion gallons of domestic SAF production by 2030, and roughly 35 billion gallons of domestic SAF production by 2050. I'll talk about at the end of the deck where we are, or where we could be with this 3 billion gallons of domestic production by 2030. And if we hit 3 billion by 2050, I think if we hit 3 billion by 2030, I think 2050 is going to be very easy, or much easier. So if we look at what I think of as the four competing net zero aviation technologies, one is batteries, the other one is hydrogen fuel cells, and the last one is hydrogen combustion and cryogenic hydrogen. And then the last one, the fourth one, is sustainable aviation fuel. This is, I think, a really nifty table that ATAG put together, summarizing a very aggressive hydrogen technology scenario over the next several decades. And so what you can see is, 5 different types of services that aircraft can provide, be it commuter all the way to long haul, and where they think the technology penetration could be under this aggressive hydrogen scenario out to 2050. What major takeaway to understand here in terms of this chart is that, like I said before, SAF is backwards compatible, meaning it's fungible with existing aircraft infrastructure and engines. And also roughly 73% of emissions come from medium haul and long haul flights. So the bulk of emissions come from things that are the most difficult to decarbonize when you look at this prognosis. Another nice summary, there's two other similar studies or similar summation type results. One is the SAF Grand Challenge report. You can go out and download it. That report outlines several different mechanisms to lower the carbon emissions impact of aviation. One where current technologies are diffused into service. One where new aircraft technologies are developed and diffused into service. One where operational developments can change. And then also the big wedges here is a 50% uptake of SAF reductions and 100%. So you can see, there's other new aircraft, there's new technologies that can make an impact, but the biggest levers for 2050 decarbonization is sustainable aviation fuel. Boeing also has a model called the Cascade model, and you can go online. This is actually interactive, and you can change how aggressive these other scenarios are with renewable energy and all sorts of other toggles. And more or less, if you play around with it, you reproduce something very similar to the plot from the sustainable or the SAF Grand Challenge roadmap. All right, a question I get almost all the time is, okay, how sustainable is sustainable aviation fuel? And in particular, I got a lot of questions about purpose-grown crops and corn ethanol. So I always like showing this slide. This is a slide from a high school, very good friend of mine, Eric Fry. It's funny how the world is. Now he's a vice president of finance at GEVO, and we touch base all the time with this stuff. But what you can see here from this slide is, let me get the laser pointer out. We have a metric for carbon intensity, so this is how much carbon emissions there are per megajoule of energy produced. And we have different mechanisms here, I hope you can see in the back, for calculating how much carbon emissions are generated in that process, and then correspondingly, how many carbon emissions are reduced when we apply other green technologies. So roughly speaking, fossil jet fuel releases about 90 grams of CO2 per megajoule of energy that's used. If you use current farming practices with and produce ethanol using grid energy, you release about 71 grams of CO2 per megajoule of energy. There is this ethanol to jet process, which was actually developed in that building that I'm in Richland, and is currently being commercialized by multiple companies, including GEVO. But if you take that corn ethanol and you produce synthetic jet fuel to be blended with fossil jet, you accrue another 24 grams of CO2 equivalent. You add these two together, and you can see that actually using grid energy and current farming practices without sequestering CO2, you actually end up releasing more carbon on a megajoule basis than fossil jet. But there are opportunities to decarbonize that mechanism to make corn ethanol. So if you use renewable electricity, you reduce about 18 grams of CO2 per megajoule. If you are creative with how you run your biorefinery, you can reduce, again, another 36 grams of CO2. If you use renewable hydrogen, you lose another 5. If you take the carbon dioxide that comes out of the fermentation process of making corn ethanol and you sequester it, you lower the carbon intensity again by 32 grams per megajoule. There are ethanol refineries that are actually on top of carbon sequestration geologies. So for some plants, this is easy to do. For others, it is difficult and may require pipelines to get that benefit. And then there's other agricultural sequestration where you use smart agriculture, whether it's targeted glyphosate or other renewable ag practices, and you actually can reduce the total amount of CO2 emitted to a negative 26. Now, these are a lot of steps that have to happen in order for this to happen, but this is one path for corn ethanol for direct CO2 emissions that could reduce the impact. There's another term involved in the calculation of carbon emissions from purpose-grown crops called indirect land use change that I'm not going to talk about today, but I'm happy to talk about it during questions at the end. Another very common question that we get when we're talking about aviation fuel or SAF in the U.S. is, do we have enough bioresources for SAF? Well, it turns out for the U.S., yes, there is the potential. This is not true for other continents. It is not true for a lot of places in the world, but at least in the U.S., we tend to have lots of biomass and lots of trash that can be converted into lower carbon fuels. And so this is stacking up a 2050 liquid transportation fuel comparison versus the amount of potential sustainable biomass converted into transportation fuels. Again, this is a lot of if, but it shows potential. So basically you can see where the biomass eclipses the combination of, rail, aviation, and marine, but not all of off-road or diesel or gasoline. Okay, so another thing that is really, really driving a lot of commercial activities within the US and Europe are the different regulatory practices. So the US passed the Inflation Reduction Act. You all should be very familiar, if you're an engineer that cares about sustainability, the Inflation Reduction Act should be the top of mind when you think about the rollout of renewable technologies across the US. And that model for the Inflation Reduction Act uses carrots. It gives you a benefit when you reduce your carbon emissions, okay? So for every gram of CO2 you reduce for your SAF, you get a certain benefit for it. It's a incentive-driven program. European models are a bit different, where sticks are typically what's referred to there. So you have to pay if you do not meet certain targets. So for those of you that are in, work in dynamic systems, this is a very interesting problem. Because in theory, if you meet the sustainability targets of both the US and the EU, you may be able to make your fuel here and ship it to Europe. And that may happen or may not happen. The amount of commercialization projects right now in the US is a lot when it comes to SAF. And I'll talk a little bit on the next slide about some of that. But these policies are driving a lot of what the commercialization market looks like at the moment. When we look at SAF production capacities, predictions, it's a bit of things are changing very fast. So this is definitely not what's going to happen to 2027. I don't want to give that impression, because so much has changed and continues to change in the SAF market. But one of the things I just want to highlight here are, basically the amount. There's a lot of projects. These are just really scratching the surface. Not all of them are always successful. Many of them are. But when you look down here to this number, and I'll come back to it at the end, to meet the SAF Grand Challenge goal of 3 billion gallons by 2030, you roughly have to double the SAF capacity every single year. What happened last year was a new plant came online that was not on this chart. And so I think we met or exceeded the 2023 doubling. There's some projects there that may or may not happen this year, but you can see we're roughly getting close to being able to meet the 2030 goal of 3 billion gallons. There's a whole mix of technologies that are on this slide. There's alcohol to jet, there's Fischer-Tropsch from municipal solid waste, there's taking used cooking oil and other oil routes and hydrogenating it and producing SAF. So there's a lot of technologies at play, a lot of feedstocks at play, and a lot of things are changing also simultaneously. But right now, that's as good of a picture, and it's a very dated slide. A lot's changed since 2022, but it's hard to pin down exactly what's going on with much prediction certainty. So, all right. So a bit more about what we do in my lab. So as a basis, safety first, safety last. If you think about the safety in terms of fuel, it's kind of like a Russian nesting doll for aviation fuels, where at the core of the safety is the fuel itself. And the fuel itself is defined with a specification. That specification then helped design the engine, what the engine can do. The engine then defines what the aircraft can do. The aircraft then defines what airlines or operators can do. And so, you can think about this initial Russian nesting doll. The importance of that propagates to all these other processes that are important for SAF. And so what has to happen is any SAF molecule, any renewable carbon, right now has to meet this original specification. The way that it meets that original specification right now, so that's the specification's ASTM D1655, is you have to blend a fossil kerosene blend component with a renewable carbon blend component. And in order to do, you have to meet a renewable, this is a SAF specification that has to meet certain product definitions, it has to meet certain conversion and upgrading definitions, has to meet feedstock definitions. So you can think about all three of these conditions have to be met to get renewable carbon into aviation fuel. And in order to do that, there is a very long, arduous qualification process where data is gathered at very early stages. This would be my lab, and communicated to OEMs. There's a formal entry into ASTM D4054. This requires about 100 gallons of fuel. There's OEM review. There's OEM recommendations for Tier 3 and Tier 4 tests. It goes into OEM review, FAA review, ASTM balloting, and finally qualification. This process right here can take up to 8 years to get through. Just entering this process right here, I have been told from one large established oil and gas company that it takes about $100 million just to get here, to produce 100 gallons of fuel. By the end of this, you may be asked to produce tens of thousands, right? And that costs correspondingly lots and lots of money and time. And so what we really focus on is this early stage testing so that you get through this as quickly as possible with the least amount of friction and uncertainty as you move forward. Let's see here. To date, there are 8 established annexes, and there are many, many, many candidate pathways that are currently being entertained. A lot of these acronyms, not necessary for this conversation, but they're they're relevant to the field. And then there's ways that you can take renewable carbon and co-process it with fossil carbon and also get a lower carbon fuel. And so this is another route, but this route also has to go through this long process nonetheless. So so there's lots of different ways to combine renewable carbon with a process and get a fuel. What I want to take away here is that when we look at various sustainable or low carbon routes, they many times are missing certain key components that fossil fuel has. So specifically, fossil jet tends to have a certain fraction of aromatics, a certain fraction of cycloparaffins, these are type of molecules, and a certain fraction of N and isoparaffins. And this blend basically is what engines and aircraft were designed around. When you have this kind of generic composition, things tend to have certain properties, and the design of these systems are built around experience. But when we look at other renewable routes, they tend to be lacking certain chemical compositions. And so the way that we describe this under CAFE, and it's great being in the state of Washington, is with apples. So we can think about a fossil jet as being a green or a red apple. Red apples, more or less they taste the same, and they taste like red apples. Green apples are things that are very similar to red apples, but there's something different about them that make them distinguishable. And then the last one is a banana, which is just wholly different from an apple. It ain't going to be, it's nothing close to what fossil jet is like at all. And so there's 2 current routes that by and large are something like red apples. There's a Fischer-Tropsch synthetic kerosene with aromatics, and there's the CHJ route, which also has aromatics. But most of the routes, and we'll talk about this later in a couple other slides, are green apples, where they're very similar, but they're not quite the same. They will not be drop-in. They will not be able to be blended, or they will not be able to be used directly in an aviation infrastructure, engine, aircraft as a drop-in fuel. And then lastly, there's bananas that are just, they're single molecules. Jet fuel looks nothing like this. It's from a biological route. It will never be used as a drop-in fuel. But there's also ways to take green apples and combine them with bananas and make a red apple. So very high-level chemistry lesson for SAF. So another major research area in sustainable aviation fuel and aviation writ large is the impact of contrails. So contrails could be more important for the radiative forcing associated with aviation than CO2 emissions. So here this is showing a contrail, a potential contrail radiative forcing impact versus CO2 emissions. And you can see that the error bars for contrails is very large, much smaller for CO2, and this contrail impact could be more important. Well, it turns out that contrails are formed in part by condensing water and forming ice that forms contrails that then forms persistent cloudiness, and it starts with the soot. So basically a red apple that has aromatics is more likely to form soot, is more likely to have water condense, is more likely to have that water form a contrail cloud that then goes into a persistent cloudiness that then reflects long wave radiation back to the Earth's surface. And so this is another very large potential area of research. So the idea being, and I'll close on this later, is can these red apples or can green apples minimize the amount of ice particles and contrails formed by aviation? So this is just an example of a potential 100% drop-in SAF versus Jet A, and you can just see, we have ways to measure this, but you can visually see a difference. It's very apparent that the SAF non-aromatic fuel soots much less than a fossil fuel. And so the question is, we have all these different balances of all these different properties. How do we design them to be 100% drop-in while minimizing NBPM? And it's not easy to do that because this is an eye chart, but there are hundreds of properties that are important. Roughly 55 of them can be calculated from individual properties of the fuel. And so it's not easy to do, but it's something that we've spent a lot of time on. You can think about the composition and impacting a cascading array of different properties. And so what we do in the lab is we really focus on trying to find very specific compositions of novel, sustainable aviation fuels. So here we have two different molecules with the same carbon number, 2-methylnonane and 2,2,3,5 tetramethylhexane. And these two molecules have very different properties writ large. They have the same number of carbon atoms in them, so when they come out of a conversion technology, this may be all that they know, or they may not even know how much C10 isoalkanes they have. But they have very different properties like the derived cetane number, how easily that fuel autoignites or not. They have very different properties in terms of surface tension, right, for secondary breakup. Very different properties potentially in terms of density, flash point, viscosity at -20, viscosity at -40. Heat of combustion is going to be pretty similar, a little bit different. Freeze point could be dramatically different, and so on and so forth. And this is the same for all these different hydrocarbon molecules that could be in jet fuel. So here's the density range for Jet A. The upper limit is the red line, lower limit's this lower red line. And you can see that different isomers can have dramatically different densities for the same carbon number. So what we do in the lab is we receive and try to identify very specific isomeric compositions. So this is a fuel that's undergoing qualification right now called synthetic aromatic kerosene. And so we did a study where we wanted to try and identify specific stereo and structural isomers in that fuel and then predict the properties. So this is just an example. You can see where I think this is the F peak here. So this is a GC-GC chromatogram. All you need to know is that there is an amount of carbon that is coming out in each of these peaks, and that carbon is specific to one or a few types of hydrocarbon molecules. And so here in this F peak, there are 2 structural isomers of methyl ethyl benzene. And when you know what those structural isomers are, you can predict properties much, much more accurately. So this is an example of when we have this spectroscopic information to identify isomers and we do not have that spectroscopic information to identify isomers, we get very different predictive results and corresponding uncertainties. And so, just an example of this particular technology we developed, it was featured on the cover of Jewel a bit ago, and we used this exact prediction. So when we understand what the chemistry is of these novel SAF routes, we can facilitate the acceleration or mitigation of certain deleterious impacts when we know exactly what's coming out. We don't always know. Sometimes we can figure it out, but when we do that, we provide this type of information to producers. So this is what we call a standard panel plot, where we illustrate a candidate fuel's chemical composition based off of different hydrocarbon classes and the associated properties associated with respect to different specification limits. And then we describe to them how to read these type of charts. So this is something that we do almost multiple times a day, more than once a day on average right now. And then, sometimes a producer could have a very high carbon number in there, and you say, okay, you have a lot of C18 molecule. You need to remove that. Oh, well, if we change this catalyst condition, then we can change that composition, or if we change this or that, we can move these things around. And then once they do this, they're able to accelerate their technologies much, much faster. A key concern for getting rid of aromatics and minimizing sooting is the dielectric constant. The dielectric constant is using capacitance gauging. And historically, there's been just a few databases that illustrated the relationship, this Clausius-Masati relationship of the dielectric constant -1 versus the dielectric constant 1 over density. And, what is the impact of sustainable aviation fuel composition on this relationship? The gauging systems have been built around effectively this line. What happens when we change the composition? And so, this is just some of the stuff that we do in terms of predicting things. And it turns out that there can be dramatically different dielectric constant measurements across various sustainable aviation fuel streams. What's interesting from these 4 highlighted boxes here is that all 3 of these molecules effectively have the same sooting propensity as each other. But if you look at this molecule up here, this dimethyl benzene or paraxylene, you can see there's a lot more leverage that we blend in this molecule. You can get these other ones into this sweet spot and still have the same TSI. So this sort of information is really important. Okay, we can have 0 to very little aromatics in this fuel and still meet the dielectric properties we need, still hit the soot, so on and so forth. But we do a lot of this type of work. So I just wanted to highlight a couple different collaborations we've had. Over the last several years, this is some work with Captus Air, Kim Tooten. Kim's been working on a technology where they capture terpenes from wood drying. So in the southeast, when they dry lumber, terpenes come out of that drying process, and it's an EPA-regulated emission. That means they cannot just exhaust these terpenes into the environment. They have to get rid of them. They have to burn them or capture them some way before they can emit this effluent. So what Kim has developed is a technology to capture the terpenes and upgrade them into aviation fuel. It's not going to solve the SAF Grand Challenge, but 40 million gallons a year is still something, right? So her technology is able to reduce the amount of natural gas that is needed to burn these terpenes before they can be emitted while producing some sustainable aviation fuel. Another technology that is we're working with several partners on is hydrothermal liquefaction. So this is where you take human waste and you convert it to jet fuel. And the algorithms are working when this is like my suggested news feed almost every week about poo in Britain, because this company is a British company and I get recommended to read these articles all the time now. So, but it's an issue. There's leaching into waterways, crops. They will use sewage sometimes, treated sewage on farm fields, which then leaches into waterways too. It's a problem. So this company, Firefly, is what one of the institutions we've been working with. This is, so basically you take wet waste and you put it through hydrothermal liquefaction. You get this material, which is a biocrude that is very similar to fossil crude. You can upgrade that into jet fuel. PNNL has been a leader in hydrothermal liquefaction. They have a pilot facility in Richland. So we've been working with them as well on this technology. This is taking a liability and making it into some kind of asset. Very interesting stuff. Another company we're working with is Air Company. We were not on their EPA Green Challenge Award, but they also won last year. And so we showed up to the rewards ceremony and it was embargoed and we're like, hey, we know staff. So this is Stafford Sheehan, their CTO, and Anna Oldani, the chief scientist at FAA. And so Air Company takes CO2 and they have 3 commercial products right now. They have a hand sanitizer, they have a perfume, and they have a vodka, and they also want to make jet fuel. And so naturally, right? So that's another interesting just example technology that I'm sharing here. There's a lot of, no, I do have a slide on that later, so I won't go back. I'm just gonna click ahead. All right, so a lot of people, when we're talking about non-drop-in fuels, what's the time horizon for those non-drop-in fuels, if ever? So this is just an illustration I put together where we have a bunch of aircraft right now that are flying on red apples, and they cannot fly on green apples. And if we want planes to be able to fly on green apples in the future, which minimizes the environmental impact, we need to do a number of things in the future. And so we have to develop a specification for non-drop-in fuels. This is an active area of work at the moment. We need to design an airplane around those that new specification, those drop-in fuels. We need to certify on those non-drop-in fuels, and then we need to start to build and disseminate or just use these green apple planes. And this needs to happen for quite some time before hypothetically you could switch over an entire infrastructure to this non-drop-in fuel. So this is something that could happen 2040, 2050, 2060. It's a very long time away. Just 2 more or 3 more slides. Washington State right now has a lot of SAF activity in terms of commercialization. There's 3 projects that have been announced, I think all within the last year, one with BP at Anacortes, one with 12. It'll be their first pilot facility in Washington State in Moses Lake, and then Skynergy Americas is looking on the eastern side of the state. And because of the work of many predecessors at WSU, I think Washington has a very strong policy framework for SAF. And then finally, I'm just gonna, in terms of our work, I'll mention this, that we're looking at developing facilities at Payne Field with Snohomish County. What we're looking at doing there immediately is developing a SAF repository. So what is SAF? Well, as I've mentioned, there's lots of different ways to produce it, right? Different feedstocks, different processes, different products. Like many other fields, we need reference materials to work with, right? And so the repository is looking to define reference materials for distribution. So you know what a synthetic paraffinic kerosene is from HEFA, like a reference, and you can design your hardware around this. So we're looking at developing a sustainable aviation fuel repository. We have a temporary site located and a permanent site also located, and we're looking at seeing where we can take this long term. And then finally, as an academic, it's always risky putting up things that aren't true, but still, I just think this is a very interesting analysis that Boom did some years ago, where it looks at the commercialization trajectories of wind and solar. So wind and solar here, as in comparison to that slide I showed you earlier from Kathy in terms of all these different commercialized projects. So you can see here's the data right here, and so you fit those trajectories to this line, and you can see that it is possible with the solar trajectory to meet the 3,000 gallons. It's not with the not with the wind trajectory. And anyway, so we'll see where this goes. I thought this was interesting, and just in terms of comparison with the two SAF Grand Challenge marks there. So with that, I'll end and take any questions.
What's the chemical formula of terpene?
Terpenes. Terpenes are C5 backbones, so you can have 10 carbons, 15 carbons, 25, so on and so forth. So 10 carbon molecules are pretty close to the sweet spot for kerosene. But they're only, for that process, there's only one type, so it's not like it would be a super high blend ratio fuel. It would be more like a banana, I guess. Yep.
You mentioned that, see the slide with all the bananas and green and red apples, that the majority of the new fuels being produced are green apples. Are they currently being produced and combined with typical jet fuel, or obviously the goal is to have both green apples and bananas combined to make a similar type?
Great question. So right now, those green apples have to be blended with fossil fuel at a certain ratio, at least. And then there's also a list of properties that also have to be met. But they're limited in terms of how much they can be blended into conventional fuel. 50% or less right now. There is a drop-in 100% SAF specification that's being written right now as well. And so a few of these will be allowed. These red apples, there's another one, will be allowed in the near future for 100% drop-in SAF. Yep. Thank you. Yep.
Hydrogen has advantages that we like, but it also has some real substantial disadvantages. There's the cryogenic storage and the fact that it's not a dense liquid, so you need larger volumes for the propellant tanks. I've heard another aviation expert say, given that he would put the emphasis on sustainable aviation fuel, that that's the more viable path forward, not hydrogen so much. Do you have a opinion on
Yeah.
that?
So there's a lot of obstacles for any dual fuel airport or something like that, for example. There are technical, there's practical, there's a lot of challenges. So this is the slide I was getting to here for hydrogen aircraft. So there are advantages. One big advantage with hydrogen right now is that economically it appears to be cheaper than doing direct air capture and power to liquids. It's substantially cheaper than that. But yeah, there's a long road. Yep.
Direct air capture, you mean capturing CO2 from the atmospheric air
Yeah.
and converting
And
it
then
to-
upgrading that to
with an
aviation
FT
fuel.
process or something.
FT or the air company technology or 12, yeah, yep.
I found that 8-year qualification timeline pretty striking, especially in light of the fact that some of these targets are within 7 years or 27 years. Is that backing up the pipeline yet, or are there?
Oh yeah, yeah,
Already it is. Okay.
yeah. Yes, it's something that I have spent a lot of time on, to be honest. 7 years trying to speed up that process, and yeah, I mean we're doing work on trying to build other ways to get fuels approved through ASTM and stuff like that. I don't want to give too many details because this is, but yeah, there's a pathway right now that's in this mix that, if it was approved, could be tens to hundreds of millions of gallons of additional SAF this year. So, and it's not happening because, and I don't want any, this is a very tough problem that we're very fortunate to have lots of very smart, hardworking people look at this, but there's just a procedural, way to do it. So, yep.
Actually, this is coming even from materials too.
Yeah, could you talk a little bit about the differences and advantages or disadvantages of hydrogen in either a fuel cell context or hydrogen combustion as it relates to aviation? And then as a second question, you made a point toward the end about differences of a predominantly solar energy versus wind energy renewable portfolio being either good or bad for aviation fuel development. And I would like to get a little bit better explanation for that.
Yep, thank you. Good questions. So in regards to those 4 different technologies, so batteries, you're carrying your oxidizer with your fuel. So it's going to be hard to match the energetics of anything that doesn't carry an oxidizer, right? So then when you're talking about hydrogen fuel cells and hydrogen combustion, hydrogen fuel cells, you can get benefits in terms of, my understanding is benefits in terms of lower maintenance costs, and you can get potentially cheaper fuel, right, via electrolysis than what you can get for some SAF technologies. So it's cheaper, but you may be limited in terms of your range versus SAF. Cryogenic hydrogen combustion, I would say the TRL is a bit lower for a lot of different things, both for hydrogen fuel cells and cryogenic hydrogen you're going to have at airports. a different fuel system, different ways to fuel the plane, to move people and goods on and off the plane. There's a lot of things that will have to change in that regard in addition to the TRL. There's uncertainties in regards to hydrogen combustion and nitrous oxide emissions, which at least one paper I read suggested was worse than NBPM for cardiovascular health. And so hydrogen combustion tends to have higher NOx emissions. And then you have the contrail impacts too, that is uncertain because you're emitting water, which could form contrails more easily, but you're not emitting NBPM, which may not form contrails as easily. So there's work that's being done to try to predict or manage, these different cost functions associated with these different technologies. So that's just a few things to compare and contrast. The last item, your second question, I apologize for not speaking clear on this. This is referring to if you match the commercialization trajectory of wind and solar with SAF rollout. So there's a annual rollout rate, historical rate for wind and solar, and if you map those onto the projected SAF capacities that I showed earlier, these are the two lines that you get, the yellow and the gray. So there's some historical trend for how fast wind and solar have been commercialized, and if you map those onto what data we do have for SAF.
So in other words, the solar trajectory would provide the energy to make a SAF transition feasible.
It's just how fast did solar roll out, and then you say we're going to take that trend line and put SAF data on it. It doesn't have to do with how much energy you're getting from these different renewable technologies.
Oh, okay, so you're just simply comparing those as like analogies for how SAF would develop.
Yeah, like how fast could we expect SAF to develop if it matches the commercialization trajectories of wind and solar? Yeah.
Is the current investment in SAF in line with either of those?
So the interesting stuff, the numbers are just gigantic, at least in terms of my own mind, in terms of how much money it costs to do this stuff. Mm-hmm. So for the facility, the SkyEnergy facility, $600 to $800 million for roughly 600 to $800 million for a 30 million gallon facility. That's how much it costs. That's a good amount for 30 million gallons, which is effectively a tenth of what we need, or a thousandth, of what we need. And what I have heard from the financial community, it's not as much that the money is not there, it's the certainty in terms of making a profit from those investments. That's one of the biggest hurdles. In addition to just having technologies that are fully commercialized today. Right now, out of these 8 different mechanisms to make SAF, one is fully commercialized. And that one can maybe produce 700 million gallons of SAF in the US in total. You have to unlock other pathways to grow that from 700 million gallons to 30 billion gallons. Corn ethanol, roughly speaking, is about a 15 billion gallon wedge that could be added if it's done sustainably. So that's another wedge, and a facility just opened up last month, or was it last month? Today's March. I think it was January, so it would have been 2 months ago. In Freedom Pines in Georgia, that's the first demo scale facility for the ethanol to jet pathway. And so that's one, and it's large. I think it's between 7 and 10 million gallons that facility will be able to produce. But building that facility takes a lot of time. You have permitting that has to be done with all this too. So there's just a lot of uncertainty, and you have to make profit on these things over 20 decades, right? So so when people are looking at investing money, it has to be something that's going to make a return for some time, and it's a lot of money, right? Yep.
So it seems like the SAFs are being developed for commercial and airline operators, but is there what do you foresee for say the general aviation or military operators in using these SAFs?
So the one thing, so once the fuel, the SAF right now is blended with fossil jet, and it's done properly, and it meets all the specification, it is fungible, which means it can be used anywhere. If you fly out of LAX in the last, I don't know how many years, you had some on your plane. There's, I don't know how many flights have been flying on the HEFA pathway. So, yeah, there's no concerns. Like I said, everything equivalent or better. I mean, it takes 8 years to get through the qualification process. There's a lot of eyeballs. So, yep.
So have you considered, along the same line, a route towards military applications, and would that shorten the qualification?
It actually, the only, at the moment, there are, the military for at least one SAFway is not allowing it. Yes. So there have been some pipeline issues with NATO and I think Colonial, because they go to military operations. So so it's actually been the opposite impact. But the military, the U.S. Air Force, none of this would be around if it wasn't for the military. The U.S. Air Force in particular spent a lot of money investing in getting the first 2 routes approved. And if it wasn't for them, spending and making this, we wouldn't have this whole infrastructure, this whole process. They really did a lot. Yep.
We have time for one more question, quick one if we have one. If not, go Dave.
Is there any indication that companies trying to develop SAF are looking to sort of get the Inflation Reduction Act carrots by, say, incorporating some of the green apple fuel into their fuel?
Oh, yeah.
While having no intention of actually making fully renewable red apple sustainable fuel?
So if they make the green apples or even bananas, they get the credits, because those fuels are then blended with Jet A. They only get the credit for the volume that they made, right? And you only get the credit for what you use, commercially. Because when we're talking about the SAF repository, we may not get any of those IRA credits. We may have to spend more money because we're using that fuel for research, not for transportation. So
they might make more money. They might just make more profits by getting the carrot, and then they might burn more non-sustainable fuel, it seems like.
No, they'll burn less. Yeah. The thing with SAF is that it does cost more to make it. You have to collect materials, and you have to upgrade them to the quality of product for SAF, and that costs more money. Yep.
All right, let's thank our speaker one more time. Josh, a little token of our gratitude.
Thank you.